In this lecture, we are going to talk about page table implementation issues and specifically compare single level pages versus, as we will discuss in a second, two-level pages. Okay, and we will also discuss some other structures that are proposed in the literature and sometimes used in the practice as well for better memory usages and efficiency purposes. Okay, so let's start. Okay, so just to understand the problem, let's start with an example, and I think this is also a good exercise for you guys about the previous chapter we discussed. So let's assume that our logical address space is going to be given in some numbers, usually in the range of these values, and the page sizes usually varies within these numbers, right? So if I know these numbers, I can easily compute my number of pages simply by dividing the logical address space by the page size. The trouble with that is in the single level paging, that whole page table should be allocated contiguously in the physical memory. So let's just say this is our physical memory, right? And let's just look at a specific example. Okay, so let's assume that the logical address space is to the power 32. So we are using 32 bits in our logical address space. Simply that means 4 GB logical address space. And assuming that the page size is to the power 12, 4K, then we can easily find out that the number of pages we will have is by dividing these two numbers, that will be to the power 20. So this 20 here is important, right? Because that tells us how many bits are needed to address each page, okay? Because we will have that many pages. It's like a 1 million page we will have in our logical address space. It's a huge logical address space, basically. Okay, if each entry, page table entry, consists of 4 bytes, then what will be the size of the page table, right? So we will see that this is going to be 4 megabytes. So how did I get this 4 megabyte? Basically, if I assume that this is my page table, right, with the assumptions that each entry, remember in each entry we have F bits for the frame number plus some control bits, and this total number of bits should be enough to store within 4 bytes, right? So that's where this 4 comes from. Right now I did not give anything about the physical memory, but assuming that F is a big number, so that's why you need at least 32 bits to cover F bits and the control bits. But anyway, so that's an assumption we are making right now. So each entry has 4 bytes, and I have to the power 20 or 1 mega entries. So that's where this 4 megabyte comes in, right? So because then I need that much space to be able to maintain 1 million page table entries, basically. Okay. So now, since I have that many entries in my page table, and if I would like to store that in the physical memory, remember, which will be divided into same size frames. So each of these frames is going to be 4. What was my page size? Okay, my page size was 4 kilobyte, right? So each one is 4 kilobyte. So what I need to do is I need to divide my page table into 4 megabyte divided by 4 kilobytes. So I will get to the power 10, or in general 1 kilo, or more if you want to use the actual numbers. It's that many frames I need as to store just my page table. But the trouble here is we have to allocate that physical page table in a contiguous manner. So somewhere in the OS needs to allocate, starting from somewhere, it needs to identify 1024 frames in a contiguous manner. And that was, remember, that was the problem we were trying to solve in the first place. Okay, so that's the trouble. Okay, what can be done? What should we do to avoid or solve this problem? Because we need that much space anyway, but right now I just don't want to store all that information in a contiguous manner here. Okay, what do you think we can do? here is the idea. Basically, let's say if this was my single page table, right, then each of my entries would be pointing the frames. The trouble was in the previous example, I had to allocate that whole thing in a contiguous manner somewhere in the memory. But if I decide to do this one, if I divide that memory into pages, right, let's say these are my pages, and of course there will be many, we're just showing 3, then what I can do is actually I can store each of this into a different frame in the memory, and then all I have to know where these frames are, that the part of the page frame, the page table frames are, and for that one you need to have another page table, and hopefully that page table will be much smaller than this one, so we can allocate that page contiguously in the physical memory, and then each entry here will point to a page or a frame that contains the page table entries basically for us, and then the second one will point another page table entry, and now this can again be anywhere in the memory, doesn't need to be contiguous like this. So that's how we can solve this contiguous allocation problem in the context of kernel as well. Simply the idea is we are recursively using the same idea. Now we are paging the page table basically. Okay, why this is good or bad? First of all, this is good because we don't have to allocate that whole table in a contiguous manner. So now we can break it into pages, and then each page, part of the page table can be stored at different places in the physical memory, and the outer, a little bit smaller page table, which needs to be contiguous by the way, can point to this part of the page table. And by the way, if that page table is big, we can further divide that one into, again, similar size of frames, pages, and then we can store all these things in different places in the memory and have another, maybe a little bit smaller page table to access each of these pages. So that will create a 3-level paging system basically. So that can continue. Okay, that's one good thing. The other good thing is not maybe clear at this point, but here is the idea. If I just use a single level page table, right, then I have to allocate that whole page table. And then whether I need all these entries or not doesn't matter, because I have to allocate that whole page table. But in a hierarchical thing, if let's say, if I know that after allocating the second, let's say just the first level page, right? So after allocating that first level page, and if I just need to use this one, and this one, assuming that this 3 second level page will be enough, and then other pages are not needed, so I can just say these are not needed. So in the second level, I don't need to allocate all the pages, right? I can just limit and allocate just enough, or the required number of pages, to make sure that little program can run. And when you get larger programs, of course, then you will use all of these things plus that outer page. Okay, so all these are good things about the hierarchical paging. So the real problem with the hierarchical paging here is, as you can guess, since we are storing first level page and the second level pages in the memory, and to be able to access each of these entries to figure out the frame number of our actual instruction or the data, what we need to do, we need to first access the outer page, right? And based on the content of that outer page, I can access the second level page, right? So that's the first plus another one. And then finally, by resolving the addresses here, I can access the data. So now it will take 3 memory accesses every time when we try to access an instruction or the data. So that's where we will now create another problem, and we will see how we can solve that problem as well. Okay, so before getting into this speed up problem, let's just first look at an example and see how 2-level paging system can be designed, right? So let's just use actual numbers here. So we are going to assume that our physical memory has 2 to the power 24 bytes. So it is like 2 to the power 4 times 2 to the power 20. So this is like mega, right? 2 to the power 4 is, yes, 16 megabyte physical memory we have. And then we are assuming that our logical address space has 32 bits, and our page sizes are just 1 kilobyte. It's small pages. So how big the logical address space is? Again, it's to the power 32, which means is like to the power 2 is to the power 2 times to the power 30. So you can think that one is like 4, and this is gig, so 4 gigs. So our physical memory is 16 megabyte, and our logical address is 4 gigabyte. Clearly, this is much larger than this one, and you cannot really run any large programs on the systems, but we will discuss that later on in the next chapter, how to deal with such big programs. But right now, let's just look at the single level page and two level page issues and see what are the benefits of these two designs. Okay, so using these numbers, I would like to ask you guys to first pause the video for a second, and I think this is a good exercise for you guys to figure out what's the number of bits for a page, what should be the offset number, and what is the size of each page table entry, and then we will compute what should be the size of just a single level page. Then we will show the two level page. Okay, so pause the video and work on these numbers. I hope you get the following numbers. First, the easy way to do it is actually first figure out based on your page size, which is 1 kilobyte, you can represent that one like to the power 10, right? So that means you have 10 bits to represent every byte within a page. So that's why your offset number of bits for the offset should be 10 bits. So once you find out you have 10 bits, then you had 32 bits logical address. So we're going to use 10 bits for offset. So the remaining bits will be used as your page number bits. Okay, so that's where this 22 comes. And then now we would like to also know what's the size of the page table entry. In this case, remember in the page table, we have to maintain at least F bits and some control bits. So in this system, what should be the value of F? How many bits we need for the physical memory? Okay, so again, let's say we have 24 bits in the physical address space, and we are going to use 10 of them for offset. So the remaining 14 bits will be used here to access the frame number. Plus, let's assume we have 2 control bits here, so altogether we will have 16 bits. So I can assume that we will use 2 bytes. Okay, so that's where this 2 bytes comes here. Okay, so with that, now what will be the size of if I just create a single level page? Remember, each entry is 2 bytes, and then all I need to figure out how many entries I have. I have to the power 22 many pages. So the total size of my page table is going to be 2 to the times 12 times 2 bytes, because that's gonna be like an almost 8 megabyte. Okay, and assuming that you have 1 kilobyte pages, so this 8 megabyte page table will fit into 8 megabyte divided by 1 kilobyte, so you will get like 8 kilo pages just to hold, or 8,000, almost 8,000 frames or pages just to hold your page table. Okay, and that needs to be contiguous, right? So that's where the whole problem is. Okay, what did we say? How can we solve that problem? We said we can solve this problem by paging the page table. So basically here you have a very large, a single page table. But we are saying instead of storing that in a contiguous manner, what we can do, we can divide that page table, right? Page table into pages. And since our pages are 1 kilobyte, right? I need to make sure that this is like 1 kilobyte, this is like 1 kilobyte, this is like 1 kilobyte, etc. Okay. So then I can now, to be able to store each of these pages at different location is a frame, I need to create another level of page, right? And then in this page, I need to know what is the frame number for that page that I store here, and maybe some control bits, right? Similarly, what is the frame number for the second page and where it is stored, etc. So this way, now we can store our information in all that information in a non-contiguous manner, and that's the goal. Okay, so that idea is clear. So now let's look at how many bits you need to address the entries here. and how many bits you need to address entries within each page. So that's why we will divide our 22-bit address into two parts, and we call them like this. Okay, it's like first level paging. I will call P1 and P2 bits, and then of course these D bits will be your offset number anyway. So here the question is, what should be that P2? Remember what I did? I divided my page table entry into 1 kilobyte pages, and the size of each page here is 1 kilobyte, right? And the size of each entry will be 2 bytes, so I can divide that one by 2 bytes. So that will give me, if you think like this, 2 to the power, if you think that one is like 2 to the power 10 divided by 2 to the power 1 bytes, so you will get 2 to the power 9 entries, right? So you need 9 bits to be able to address every entry within that table. So that's why this number P2 should be 9. And we know that this number was 10. So the remaining bits, whatever remains here, will be 13 bits. So you need 13 bit to access the first level page table, and then the second level page tables, each one will be 1 page. So we need to find out enough number of bits to address every entry within that table. So that's why it is 9. Okay, so now with that we can easily compute what these numbers are, right? That's where this 13 and 9 comes. Okay, so with that, all these things, now what happens is we are going to divide our logical address all together into P bits, P1 bits, P2 bits, and D bits. And why this number is 9, as I explained in a second, because in the second level page I will have that many to the power 9 many entries, and to be able to address each of these entries in the second level I need to have 9 bits in that level. Okay, so when you put all this together, okay, so basically what happens in terms of a picture, assuming that this is your physical memory, okay, and this is the whole frame that's holding the page you are trying to access physically, and now the page table is 2 level, right? So when the CPU generates that logical address, depending on our system parameters, we will divide to D bits, P2 and PB bits based on the address space bits. Then we are going to use this P bits as an index to that outer first level page table. Okay, and then the content of that page table, remember, is going to have F and some control bits. And by using these F bits, we will know which frame is holding our second level page table. And then when we go into the second level page table, then now we are going to use this P2. Okay, so once we know where that page table is, then we are going to use this P2 as an index, okay, as an index on this table and get the entry we want. And this, the content of that entry is again F bit plus some control bits. So we're going to take that F, and then we are going to add this D bits to it, and then we go to the exact memory location of the instruction or the data we are trying to reach. But remember, again, this is like in the physical memory, this table is also in the physical memory, this table is also in the physical memory. To reach the final value or the final instruction or the data we are trying to get, we have to go through this table, and then that entry basically. So it will have 3 memory accesses compared to just the traditional system. So it's going to be really slow, okay? Okay, so the second advantage of our 2-level paging system was, if you use a single level paging, you have to create, you have to allocate the whole page table, but if you don't need all these entries, maybe the second 2-level paging will save you a lot of space. Okay, so let's just show another example for that. So here the question is, how much memory is needed when it comes to second 2-level paging? So in this case, definitely we need the first level page, how big it is. we will find out, but we definitely need that table. But for the second level pages, we just need the enough number of second level pages, depending on our program size. If we have a smaller programs, probably we don't need all these second level pages. But if it is really a large program, then of course you need all these things. Okay, so let's just look at that in terms of some numbers again. So suppose we have a 1 GB physical memory and 32-bit logical virtual address spaces, and this time we're going to use 4 KB page size. Okay, again, I think it might be a good practice for you guys to stop, pause the video for a second and first figure out what will be the values of P and D in that system, and then F and D in that system, basically. Okay, since we know the page size is 4 KB, which is 2 to the power 12, right? So then the D should be 12 bits, right? And then since the logical address have 32 bits, then I know the remaining bits here, 20 bits, right, will be for physical address. How about this one? This had 1 GB physical memory, so this is like 2 to the power 30 bits, and I know I used 12 of them for, so here you have 32 bits, right, and here you have 30 bits for the physical address, so the remaining 18 bits will be your frame numbers, right? Okay, what will be the size of the page table if we use a single page table? And let's just assume that the page table entries will be 4 bytes. Why? Because I need F bits, right? 18 bits plus some control bits, and since it's more than 2 bytes, I will just make it 4 bytes. Okay, so just to make the computation easier. So that's why I'm assuming it's 4 bytes. But let's say with that assumption, what can you say about the page table size? Okay, again, pause the video and do the math. Okay, here the idea is how many pages do I have? 2 to the power P, which is in this case 2 to the power 20 pages I have. So then the page table should have 2 to the power 20 times each entry is 4 bytes. So it will be like 4, this is mega, like 4 megabyte table. So that just for the page table, you need to consume that much space in the physical memory. And if you look at how many frames you need to store that one in a contiguous manner, remember the 4 megabyte is the page table size, and each table has 4 kilobyte, so 4 megabyte divided by 4 kilobyte, so you will have 1 kilo frames needed, and you have to contiguously allocate this almost 1,000 frames in a contiguous manner to be able to just maintain the page table. Okay, so just keep that number in mind, and when we do the math for the second level paging, you will see the difference. Okay, so now in the next slide we will assume that the size of the process we are trying to run is 32 megabyte. So how many pages I need for the program itself and how many pages I need for the page table, we will do those calculations. Okay, first of all, for this process, it is 32 megabyte, and the size of each frame or the page is 4 kilobytes. So by dividing these two numbers, I can figure out that I need almost 8,000 virtual memory at least to just maintain this process. Okay. Okay, so now if I have 8,000 virtual pages allocated, right, in my tables, I should know where are these frames are. So that's why I need a page table. So if I use a single level page table, right, maybe only, let's say, some of these pages will be used and some of these pages will be used, and then rest of these pages will be not used, but I have to have them in my table. So now I need a huge table here. And with the second level paging, actually, we will see that actually what we can do is with the second level paging, maybe our first level page, we will definitely have this one. Then of course, this may have an entry saying that, yes, you need this part of the page. maybe you need that part of the page, and then maybe for those you need that part of the page, and for this maybe you need that part of the page. But for all the other entries, just put null, 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 means that you don't have any pages yet. And in the future we will learn, I mean, if we need those pages as well, we can bring them and put their addresses here. So with the second level paging, really what happens, instead of having such a large page table, we can just have a small first level page, and then depending on how many I need, I can just have that many second level pages. So the total amount of the information or the frames or that we will use for a whole thing will be much less than a single page level. Okay, so let's just look at an actual numbers to get this. But that was the idea in general. So we have the size of my current process 32. We divided that by this, so we get 8,000 almost virtual pages needed. So assuming that the page, assuming that each table entry is 4 bytes, and then one page can store, right? If I divide 4 kilobyte, that was the page size. If I divide it by 4 bytes, because each entry has that many, so then I can have 1K pages in a page. Okay. So basically, if I allocate one page or one frame, in this one I can have 1K entries, 1K, which is to the power 10, right? So to the power 10. So I need 10 bits to be able to access each of these entries, and each entry will, assuming that is 4 bytes. Okay. So if that's the case, and if I need to maintain that many virtual pages for my program, then how many pages I need like this so that I can have entries for that many pages, right? So that's clear because I have that many pages and each one needs an entry. And if I divide it by 1K, which is the number of entries in a page, so that dividing by these two numbers, you will figure out that actually the 8 pages, if I just allocate 1, 2, 3, total 8 pages, so that will, all these 8 pages together will contain enough entries to address every one of these pages. I don't need any more pages. So if I just maintain these pages in the second level, and then in the first level paging, page table, all I need to know where these pages are, right? And then assuming that all the other pages are not needed and I don't need to allocate space for them. So this way we can simply, all we can do is we can just allocate 8 pages for the second level, and then one more page. I think one page will be enough in this case for the first level page. First level page sometimes might be bigger than one page, but in this example it is one page. Why? Because we had, remember in this example, we had 20 bits in our physical, in our logical address space, and we used 10 of them for for that level, right? And whatever that d bit, and then the remaining 10 bits will be for the P1. So this one is to the power 10. So that means one in this system, and each table entry is 4 bytes. So this just one page will be enough. Actually, just one page will be enough to have enough entries to address every second level page that we have, basically. Okay, so that's why one page will be enough here. So, okay, altogether, remember in the previous slide, for a single level page, we need almost 1,000 frames to hold the page table. But in this case, all I need 8 plus 1, so total 9 pages, or the frames are enough to hold the page table for that process. So see the significant amount of memory will be saved, basically. Okay, but what we are losing is the memory access time, right? Because now in this case I have to access this table, then I have to access this table, and then finally I need to access the actual data or the instructions. So that's where the trouble is, basically. So anyway, overall this gives us much better space utilization compared to a single level paging at the cost of increasing the access time. What will happen if you have really a very, very large program? So of course, in that case, you will have many pages here and plus one more page. So compare the single level page table. In the worst scenario, we have the same number of frames in that level, but then for the second level paging we need plus one more pages here so that we can know where the other pages are. Okay, so just to illustrate the point one more time, what did we do? So we assumed that our logical address is 32 bits, and if we use the two-level paging, we divided it in a way that we will use 12 bits for an offset, and then the other bits were 10 bits and 10 bits, and hopefully you understand how I got this 10 bits and this 10 bits. And then the system works like this. So when that address is generated by the CPU, we look at the page table base in the process control block, and we access that frame which holds the first level page, and then using these 10 bits as an index, we access a page table entry here, and then by using the content of that entry, we find out where that page is maintained in the physical memory. And then once we get that page, second level page, then I use this 10 bits as an index on this table and find out the content of that table. And then from here we have the F bits, and we take these F bits, these 18 bits here, and then now we combine these 12 bits. Let me just use this arrows. So then we combine this together, and then whatever that address is, we use this one to go to the physical memory. Okay, so everything works nicely. The only trouble here is the speed. 1, 2, 3 times we are accessing the memory. So the question is, how can we improve the memory access time? Okay, can we use the associative memory here? Sure, why not, right? So basically what will happen here, we will insert a TLB table here, and in the TLB table, each entry will maintain the P1, P2, and the corresponding frame number for the most frequently used page. Remember, this table is small, and when these bits are presented, they are searched in parallel. If it is there, then one will hit, and from that we will get our frame number, and then by combining frame number with the offset bits, we can get the physical address and go to the memory. If the entry, the one we are looking for, is not here, then we can definitely go to the first level page, and then from this we can go to the second level page, etc. Right? So as we did last time, we can actually quantify this one using this condition, this probabilities with the condition. So we will assume that in this case, so for example, if I ask you to compute effective access time, in this case, all you need to know, what is the heat ratio here? Let's say this is, remember we said this is alpha. So with alpha, what happens is we are spending epsilon amount of time to access that table, and plus one memory access, right? So with that probability, the entry we are looking for will be in the table, so it will take that much time, and then we will actually access the memory with m units of time, right? But what if it is not there? Then we will say plus the probability that the entry is not in that table is going to be 1 minus alpha, right? And with that probability, basically what happens, we look at the entry in this table, so we spend that much time, plus then we go to that table 1, then we go to that table 2, then finally we go to that table 3. So we have 3m memory access, right? So when you add these two numbers together, that will be your effective access time in this system. So clearly, if the alpha increases, this will be like very similar to a single memory access systems very much. Okay. Okay, so this slide just simply does the calculations one more time the way I did. So in a 32-bit physical address space with a logical address space and with the 4 kilobyte page sizes, we can have each entry 4 bytes, etc. So we can assume that we will have that many pages, each entry has this, so our single level page will have that much space needed. Okay, but if I use 32-bit machine, again the same scenario, but assuming that our program requires only 8 two-level pages, that's then of course an assumption. So in this case, definitely I need one first level page which will have that many entries with the size of each entry is this. And the second level page, again, in this system has the same, but we need 8 of them, right? So to total we need 9 pages, and each page is 4 kilobytes, so altogether it will be 36 kilobytes. Okay, so now if you compare these two numbers, 4 megabyte versus 36 kilobytes, it's a huge difference in the context of that specific process, right? Okay. Okay, now let's look at another example on a 64-bit machine where let's say the logical address space is 64 bits, and assuming that in this system we are using 4 kilobyte page frames, so the offset bit will be 12 bits, right? Then if I just use a single level paging, as you can see, I can divide the 2 to the power 64 logical address space by the size of the page. Then I can have 2 to the power 52 entries. It's a huge number, it's a very huge table, right? So definitely a single page system will not work here. So what can we do? We can go a second level paging. And remember, when we are going for the second level paging, we need to find out how many entries we can have in a page, right, in that system, so that we will use for the second level paging, we will use just that many bits to address each entries on that page. So in this case, since we are assuming that we have 1K entries, because the size of each page table entry is going to be 4 bytes. So we have 4 kilobytes. It's like divide, which is 2 to the power 12, right? And this is divided by the page table entry size, which is 2 to the power 2. So here you will get 2 to the power 10. So you need these 10 bits. So each table entry is 4 bytes. And then this total size is 4 kilobytes. So within this one, each entry will need 10 bits. Okay. So then I can divide my 52 bits into 10 bits for the inner page and then 42 bits for the outer page. So we will have a page table, a huge page table again, to the power 42, and by using this as an index here, we will find out where the second level page is, and then when we come to the second page level page, then we can use this 10 bits here to find out which entry we are talking about, etc. Okay, so again, this page is so huge, so what can we do, right? So now, since we figured out that this page can be divided into pages as well, and in each page I can have 2 to the power 10 entries, so I need 10 bits, so I can further divide this address into something like this, right? So we need these D bits, then I need 10 bits here, I need 10 bits, and then the remaining 32 bits will be third level paging. And then if we continue with that logic, then you can also divide that one into 22, 10, and then you can divide that one into 12, 10, and then if you want one more, maybe you can divide it by 2, 10, right? So basically it will be something like this: 2, 10, 10, 10, 10, 10, and then the bits, right? So you can have that many level pages. So now your very first level page will have 2 to the power 2, 4 entries. So even you can maintain, for example, that table not in the memory, but maybe in the on the registers to have quickly access that thing, but others needs to be in the memory. So in this case, you will have 1, 2, 3, 4, 5, 6, and then last one will be 7 accesses needed for 7 memory accesses are needed to resolve just one logical address to a physical address. It means that each of your program, if it was taking 1 memory access, now each instructions will take 7 memory accesses. So that will really slow the programs a lot, right? But we know how to get along this problem, right? So we can put our entries, most frequently entries, into TLB table, and then try to increase the hit ratio so that we can access those pages quickly. Okay, so that is just simply showing what I discussed already. So we need 6 level paging plus 1 more, so we will have 7 memory accesses in this system. Okay, if TLB is not used, definitely these systems will not be good. So definitely TLB will have a significant impact, and specifically with the high success rate, they will have a significant impact on this real systems basically. Okay, so now people like these paging ideas and try to improve its performance, but at the same time, researchers were also looking for other possible page table structures, and we will see a couple of them now. Okay. Okay, and one structure is proposed called the hashed based page table. If you know what hash map is or hash function is doing, I think you will easily understand the idea here. So the problem here, if I just use a single level paging table, right? Remember that table needs to be so huge, and in this case what will happen is we're going to use this P as an index on that table, and we will access this P bits as an index on this table and get the frame number from here, and then combine with this D bits, right? F bits, D bits, and then we will access a physical address. So if that table is so huge, and then if many of these entries are not being used, then there's really no need to keep such a big page table, right? So maybe you can say I'm gonna keep a little bit smaller page table, but then in this case you cannot use P as an index to any of to every page that you may have, right? Because you don't have enough entries here. So then the idea is this, okay? So if I have a limited page table size, then when I get these P bits, I can use some kind of a hash function to map that P into one of the entries here. Of course, the index for that one will be the hash value. So we are going to use that hash value to access that entry. And then in this entry, we are going to say, okay, what is the page number we are working on and what's the frame number for that one, right? So if I maintain the frame number here and some bits to showing that this is the entry, etc., then when P bits are given, we can easily in O1 complexity then figure out whether that entry is in the table or not, right? And as you remember in the hashing, there's one little problem we have to deal with is the collisions, right? So what if two different page number gets the same hash value, so then you will be looking at the same index value. So in this case, instead of putting the frame numbers here, what we do, we are going to maintain a linked list, and we are hoping that this linked list will be which will have a small length, because hash function is nicely going to distribute these entries around the table. So in that case, let's see if P1 hashes to that entry, then here we will use this as a pointer, and one of the entry will say, okay, page P, corresponding frame number is R. If another page comes later on with Q and S, Q is the page number, S is the frame number, we will put that as an entry here, and then we will link them to each other. If there's any other entry, we will insert into that linked list, right? So that's the way we are going to maintain the page table, and then when the address conversion needs to be done, we will take the logical address as before. We are going to divide it into two parts, use the P through a hash function, access an entry, and then search that table to figure out whether this page is here or not. And then if it is there, then we are going to take the frame number from that entry, combine with the D bits, and we can access the page table. Okay, so I'll leave some of the details on the hashing and things like this, you guys to read from the book, but that's the idea. So the main problem we are trying to solve here is just have a single level page, and then instead of a very large single level page with using the P as an index, we will pass the P through a hash function and then use that as an index on a smaller size page table, so that we can effectively or efficiently use our memory for small programs specifically. Okay, so that was the idea. This one probably I will say this is important, and in some exams we might be asking something about this inverted page table thing. And here is the idea. If you remember let's just look at the single page table architecture. So the CPU generates an address, and we take that address and divide it into P bits and D bits, and use the P bits as an index on a single page table, and then from there we were getting the F bits, and then we were getting the D bits, and then we are finding the memory, corresponding memory, right? So that's a page table. So the trouble with this thing is every process in your program, whether they need that many pages or not, should have that page table, right? So that's going to be really a too much space consuming solution. Okay, So now the inverted page table came up with that idea. They said, okay, you may have too many pages for many programs, but at the end of the day, for each frame in the physical memory, we will have somebody's page there, right? So we will put maybe one of the process page table here. Let me just draw a graph here. So maybe this will, you will put the page 1 here from process X, from process Y we will put page 1 here, for process Z we will put page 2 here, right? So this is the way we will be using. So then the inverted page table simply says that why don't we just maintain that table for the whole system? Not for every process we are going to maintain that table, but for the whole system we will maintain a table. But in that table we should maintain two things explicit. So that will be the only table, which is called the inverted page table. And in this page table we will maintain what is the ID of the process, which process is using the corresponding frame, and what is the page number from that process, so that each inverted page table entry will have process ID. Usually it is 16-bit or 2-byte information, plus how many bits you have for your page numbers, and plus some control bits. So based on these 3 bits of information, you can compute the inverted page table entry size. Okay, then the rest is just to figure out how many page table entries you have in that inverted page table. Since you need to have 1 entry for each frame, right, in the physical memory. So let's say this is your physical memory and you divide that into frames. So for each frame in your inverted page table you will have 1 entry, and the content of that entry is going to be which process is using, so this is the process ID, and which page of that process, let's say P bits will be used for that, and then some control bits, right, needs to figure out. Okay, so once you have that table ready, okay, so then the rest is this. Okay, so when a process generates a logical address, of course this time we will also take the process ID, so we will take that information and we will search it in that table. So when we find an entry here, the index here, the index of that entry is actually the frame number for that page, because we know this entry corresponds to that frame which contains our processes page, right? So that's where that name comes from, inverted page table. So the index of the, once you finish the search, the index of that search will tell you what's the frame number basically. So that's where that name comes from. So there are a lot of advantages here, and of course disadvantages as well. So one of the key advantages here, it's very efficient in terms of memory usage, because for the whole system we just need to maintain 1 table. And the biggest disadvantage here is we have to search, because we don't know where the process ID and the process thing is, right? So we have to search through that table. If that table is very large and we are going to use some kind of a linear search here, it will be really, really time consuming to find out the corresponding frame number for a given process, right? So maybe you can think of how to continue with this inverted page table idea one more time. So here is the idea that your physical page, physical memory is going to be divided into frames, right? And then we will just maintain 1 inverted page table, and the number of entries in this page table will be this same number of how many frames you have in the system. So if I have 0, 1, 3 X frames here, then I will have 0, 1, 2, 3 X frames in that table, and each of these entries are corresponding to frames here. Okay, and the content of that table will have these entries, process ID, and of this process which page is going to be maintained in that frame 0. Similarly here, which process and which page is maintained on frame 1, etc. And of course we also need to have some control bits here, right? So altogether this will be the entry size. Okay, so that's the only page, the inverted page table you will have in the system. And then when the process generates an logical address, which will probably consist of this bits of information, right? So then we're going to take the process ID and we're going to take the P bits together, and then we will go and search this through the system. Once we find the one we are looking for, if it matches, right, then the index of that entry will be used as our frame number. So we will take this, in this case it's the 128, but it's actually a 18-bit information, so we will take this 18 bits here, and then we will copy that 12 bits here, so altogether you have your physical address and you will go and access the memory basically. Okay, so that's the idea, and let me just show. Okay, so we take this, we search it through these things, and then when we find it, we use the index of that table. That's where that name comes from, inverted page table. So we use that inverse index as our frame number, and then combine with the offset, and now you get your data. Okay, so how many memory accesses we had? It depends. If your entry was here, it took 1 + 1, 2. But if it was the this entry, and if you compare every one of them, then probably you will spend that many memory access, which is unacceptable, right? So to deal with that memory access problem, so we get this great memory utilization, right? We spend less amount of memory, but access time is really bad. So we can improve the performance maybe by using some kind of an hashing or some other techniques. I'll let you guys read this part, and I'm gonna keep that as an optional slide. On the exams or on the quiz, I think we are mainly asking to figure out what will be the size of that table, and to find out the size of that table, all you need to find out is what's the physical memory size, right? Physical memory size, divide that one by the page size. So this way you will find out the number of frames. Okay, so this is going to be the number of entries in that table. Okay, and then this basically in general, this is 2 to the power f entries you have times the size of each entry. In this case, usually each entry has at least 2 bits for process ID and p bits for whatever it is, and then some control bits. So again, try to make the whole thing as like 2 bytes, 4 bytes, 8 bytes. Okay, so you can make these assumptions here, and that will be the size of your page table basically. Okay. Okay, so let's just finish up that whole thing with a